welcome back. Now in this video we're going to look at the case where your object is traveling either greater than or less than the design speed of a track. Okay, so in that case friction will become involved because friction needs to keep the car from either sliding up and off the track or sliding down the track if it's going too slow. All right. Now, like I said before, this is going to be a bit of an extension part. It's extra, so you can skip the video if you want. It's not necessary. It's here just for completion. Your book doesn't go through this. I haven't seen a Year 12 textbook that goes through this in great detail, and if it does, it's off to the side in a little extension box somewhere else. Okay, so I'm going to go through it anyway. Watch it if you're interested. You do get a very nice result at the end, and it's not too crazy, the formula. But we'll just see how we go, how we get there and everything, okay? So, first we'll look at when the object is traveling greater than design speed. Also, by the way, this video is probably going to be longer than normal, so grab some popcorn, settle in if you need to. All right, so greater than design speed. So what does that mean? It means the car's traveling quicker than it should. All right, now if you've ever been in a car going around a roundabout and you're traveling too quickly, you might start to hear your tires squealing. That means your tires are struggling to keep you on the road. The friction is at its limit. And if you go too much faster than that, you're going to slide out of the roundabout off onto the grass somewhere, and that'll be the end, okay? So what's going on when the car is traveling at greater than design speed? The car wants to move up the track, okay? So the car wants to move up the track, okay? Now, in order for your car to maintain circular motion, there's got to be that friction force between the tires and the road. And if your car wants to move up the track, then friction needs to oppose that, okay? So the friction must point down the track to keep your car from sliding. Okay, so let's draw a picture, see what all that looks like. Okay, so here's your banked track. Here's horizontal. All right, let's call this angle theta. All right, and there's your car traveling around in a circle. Just keep in mind, it's still a horizontal circle. Okay, we're still talking about horizontal circular motion. It's just that now friction needs to get involved in order for that circle to maintain, to still be horizontal. Okay, so let's draw the forces in. We've got normal force. Normal force just always points perpendicular. You got to remember that always. Gravitational force points down. And friction in this case is going to be pointing down the track in order to stop the car from sliding up and out. Okay, so there will be this component of friction pointing down like that. Okay, and just remember the net force is still towards the center of the circle, which is over there somewhere. Okay, net force is that way. All right. Okay, so let's decompose our normal force and friction into components. So we've got a vertical component for normal, horizontal component for normal. Right, now this angle here of your banked curve, that translates into here. Okay, because we've really just rotated this triangle here 90 degrees clockwise. Okay, so the horizontal component of normal is written as Fn sine theta, just like before when we were dealing with at design speed. And vertical component is Fn cos theta. Lovely. All right, we have to decompose friction as well. So we've got a horizontal component, and you can already see this horizontal component is contributing to the net force. Okay, and we've got a vertical component. This angle theta down here, that is this small angle there. And let's label it, so that would be friction cos theta. This would be friction sine theta. Have I got that right? Yes, okay. So, let's talk about the forces. Now, there is no vertical net force. The net force is completely horizontal. So if I set up my little coordinate system like that, okay, that means when I add up all the vertical forces, they should all add up to 0, okay, because there is no vertical net force. It is completely horizontal. It's a horizontal circle. So let's do that. So sum of the forces in the y direction. Well, what do we have? We have a Fn cos theta pointing upwards. So we write Fn cos theta. No other positive vertical forces. So now we subtract all the negative ones. Okay, we've got minus this vertical component of friction. Okay, that's pointing downwards. So it's friction sine theta. And we've also got to subtract gravitational force. Okay, we know the sum of these forces is 0 because the net force in the vertical direction is 0. There is no vertical net force. All right. Now, if I go ahead and solve this for the normal force, what do we get? Okay, we're going to do a bit of algebra a bit quickly. So if you miss any steps, just try and work through it yourself. I'm going to skip a couple of steps here. But all I'm really doing is subtracting gravity and this component of friction to the other side and then dividing it all by cos and simplifying what I get. Okay, so we will get Fg over cos theta, but we'll also get friction sine theta over cos theta. And you've got to remember sine over cos gives you tan. So we can write that succinctly as tan theta, okay? So there we go. We've got an expression for the normal force in terms of gravity and friction. What good is that? Well, now we're ready to actually write an equation for the net force. And again, because the net force is completely horizontal, that means the net force is just equal to the sum of the horizontal forces. Okay, so let's add up all the horizontal forces. We've got horizontal component of normal, Fn sine theta, plus the horizontal component of friction, which is Ff cos theta. Right? That's it. They add up. And what is our net force equal to? Well, the object's in circular motion. And anything in circular motion has a net force equal to mv squared on r. Okay. Now, I'd ideally like to calculate my net force in terms of quantities that I know. Okay, now we don't know the normal force. Okay, there's not really an easy way for us to gather that kind of information. Generally, we calculate the normal force via other things like gravity and stuff like that. Okay. In this case, we've got an expression for the normal force that we've developed from our vertical net force equation. And what I'm going to do is substitute this thing here into the normal force that we've got in our most recent equation there. Okay, so I'm going to substitute all of that into there and clean it up a little bit. Okay, what do I get? Net force equals, okay, substituting normal force. Okay, well the first bit is going to be Fg over cos theta times sine theta. And you'll see sine over cos, again, turns into tan. So that gives us Fg tan theta. Then I'll be doing friction tan theta times sine theta. Okay, so that's me substituting this normal force here into there. I'm done with that now. Now I can just add this friction cos theta to the end of that. Okay, and that still is all equal to mv squared on r. Okay, now we're pretty much done at this stage, okay, because I've represented my net force in terms of gravity, which we can work out, and friction, which is generally just given to you. And that's all equal to mv squared on r, okay? We can clean this up a little bit more, okay? So what we can do here, and unless you know your trig identities, then this won't really make any sense to you, but off the side here, let's go and just factorize this first. Okay, so hang on, let's factorize this. So we'll get net force is equal to Fg tan theta plus, I'm going to factor out the friction from the last two terms. We'll get tan theta sine theta plus cos theta equals mv squared on r. Okay, now what I'd like to do, instead of having this stupid tan sine cos thing here, right, I want to write that a bit neatly. Okay, so that's what we're going to try and do, write that more neatly. So tan, and I'll abbreviate things. I'm going to, because I don't want to write tan sine and cos every single time. I'll do t theta. That just means tan theta sine theta plus cos theta. Okay. Now, what is tan? You got to remember, tan is just sine over cos. Okay, so tan can be rewritten as sine over cos. So really I've got sine times sine over cos plus cos. Okay, sine times sine is sine squared. And I'm going to write this cos term here with a denominator of cos, which means I'm going to have to multiply it by cos over cos. Okay, so that turns into sine squared over cos plus cos squared over cos. Okay, and one of your trig identities is that if you've got sine squared plus cos squared, that's going to always equal to 1. So really, this fraction here is just equivalent to 1 over cos. Okay, so tan times sine plus cos is equal to 1 over cos. And we can actually make this even simpler because we have a definition of 1 over cos that's equal to secant. Okay, so you may not have heard of that before. It basically looks like this, SEC. Okay, so I can replace this tan sine plus cos with secant. And so I'll get my net force is equal to Fg tan theta plus friction sec theta equals mv squared on r. Okay, there we go. I've developed an equation talking about the net force for an object traveling greater than design speed on a banked curve. Okay, and you can see the equation is actually not that crazy. This was there when we were talking about banked curves at design speed, Fg tan theta. All we've done now is add this extra little term here talking about the friction that's now involved. Okay, but the way that we got there is probably slightly too complicated for what you need to be doing at year 12. The actual equation though is not too crazy. Okay, so there we go, greater than design speed. So we've got this equation here representing the net force. Now, we can do pretty much exactly the same thing when we're talking about a car moving at less than design speed. Okay, now think about what happens if you're traveling too slow around a banked curve like that. Okay, what might help you visualize what's going on is if your car is sort of parked on a steep hill. Okay, why doesn't it fall down the hill? Why doesn't it just roll down? Well, that's because you've got brakes and the brakes have locked the wheels in place. Why doesn't the car still slide down? Well, that's because there's friction between your tires and the road. Okay, so the friction stops your car from just sliding down the hill. Okay, and that's when you're stationary. If you're moving too slow, friction is still there trying to stop your car from sliding down the hill. Okay, so in the case of traveling at less than design speed, your car wants to slide down the hill. Okay, wants to slide down the track, but friction is preventing it from doing that. Okay, so friction must be pointing upwards or up the track. Okay, friction has to be pointing up the track to stop your car from sliding down the track because you're moving too slowly. Okay, that's what's happening there. And again, let's draw a picture of what's going on. It's very, very similar. Okay, this process is going to be very, very similar to how we calculated a net force equation for greater than design speed. Okay, so your track is banked at some angle. Here's your car. Okay, and the car is going into the page and around in a circle. All right, and we've still got our normal force pointing up that way. We've still got gravity pointing down this way. But now our friction is pointing up the track like this. Okay, so that is friction there. Okay, and again, you got to remember this car is moving in a circular path. You got to picture this banked curve as sort of part of a cone. It's going around like that, and the center of the circle is there. Okay, so the net force is directly to the right in this case. Okay, and so we set up our coordinate system so that to the right is the positive direction, because that's the direction the net force is. All right, let's break stuff into components. So let's do our normal force. There's a horizontal component and a vertical component. Okay, and this angle here is going to be this angle there. Okay, so that means this vertical component is Fn cos theta, just like before, and this horizontal component is Fn sine theta, just like before. Okay, also breaking our friction into components, you've got a vertical component pointing up, and a horizontal component pointing towards the left. This angle here is going to be equal to this angle here. And so we've got our horizontal component equal to friction cos theta, and the vertical component equal to friction sine theta. Okay, so we've decomposed everything. Now we're ready to start analyzing our forces. So again, because your net force is pointing completely horizontally, there is no vertical component to that net force. So when I add up all my forces acting on this car that are acting in the vertical direction, they should all add up to 0. Okay, so let's do that. Let's sum the forces in the vertical direction. What do I have? Okay, so I've got this component of normal pointing upwards, so that's Fn cos theta, plus I've got this component of friction, which is also pointing upwards, Ff sine theta. And I subtract gravity because it's pointing in the negative direction. I know that they are all going to add up to 0. Okay, and again, solving for the normal force using this equation is going to give me Fg over cos theta minus friction tan theta. Why tan? Because I have friction sine theta divided by cos theta. Sine over cos is tan. Okay, so I've developed a way to represent my normal force in terms of gravity and friction. Now, let's talk about the net force. So again, the net force, because it's completely horizontal, must mean that it is the sum of the horizontal forces. Okay, so let's sum up the horizontal forces. What are our horizontal forces here? So we've got this normal force pointing in the positive horizontal direction, Fn sine theta. And I've got to subtract this component of friction, because that's pointing in the negative direction, Ff cos theta. And what do I know my net force equals? If an object is in circular motion, my net force is equal to mv squared on r. Cool. Now we do what we did before. I've got this expression for the normal force, and I'm going to substitute that into here and clean it up. Okay, so normal force is Fg over cos theta times sine theta, which is Fg tan theta. Then I'm going to have minus friction tan theta times sine theta, so minus friction tan theta times sine theta. And then I've done substituting that. Now I've just got to subtract this friction from all of that. That equals mv squared on r. And again, we can factorize. Now it's pretty much exactly the same as it was before for greater than design speed, except instead of these minus signs that you see there and there, before they were plus signs. Okay, so really the only thing that's going to change is we're going to factor out this negative negative friction. So it'll be FG tan theta minus friction, and then in brackets we'll have the tan theta sine theta minus, plus cos theta. So it'll look like that. And then you can turn that thing here using what we did there into sec theta. Okay, so really the only thing that's different is that plus there turns into a minus. Okay, so Fnet is equal to Fg tan theta minus friction sec theta. And all of that is equal to mv squared on r. Okay, there we go. We've developed some expressions for our net force when our object is traveling either greater than or less than the design speed. Okay, there we go. Again, it's an extension. All right, it's not something that I have encountered before in an exam or in any chapter questions from textbooks. I've seen it in uni, but not in year 12. Okay, so now you know at least that that's what it is. But really, you could have developed that yourself. If you analyze the forces yourself, like we've been analyzing the forces in our force questions, there's no reason why you couldn't have come up with something like that yourself. Maybe if you didn't know about your trig identities, maybe you wouldn't be in the form of sec theta, but you would get something close that would still probably work. Okay, so it's not that much of an extension. It's just that I think the work involved in developing your final expression is a bit too much for year 12 level. Okay, but nevertheless, there it is. So that's it. Right, review that if you want to. Sorry for the long video, it's just how it is. And next time we'll look at some more stuff. All right, see you then.